Hello and welcome. Today we'll be discussing section 2.2 of the textbook. The topics in this section are right triangles and their properties, trig functions, notation/terminology, as well as basic trig functions and how to solve for the various trig functions with a set of given information. So the first thing is to define what a right triangle is. A right triangle is a triangle that contains a right angle. So if I have triangle V, W, and U, my angle U is a quarter turn, which is 90 degrees or pi over 4 radians. And we denote that the side of the triangle that this box does not touch, that does not construct angle U, we denote as the hypotenuse. For the other two sides of the triangle, we will denote them as leg 1 and leg 2. Now, we are going to make everything in reference to one of these angles. So we're going to choose one of these angles and make references to it. Now, this angle V here, we will call leg 2 the adjacent leg. I'm going to call this A. For leg 1, we'll denote this as the opposite leg. Which I'll denote as O. Now, the opposite leg is determined by the side of the angle that does not construct the reference angle. So here the reference angle is again V. This leg 1 does not construct V. Therefore, we denote it as the opposite leg, which I'm going to call O. The adjacent leg, again, is a part of the construction of the reference angle that is not the hypotenuse, which is this side here, which I'm going to call the adjacent. For the rest of this lecture, when I talk about trig signs, opposite, adjacent, hypotenuse, reference this image because everything is in relation to the reference angle. So with that, we want to figure out, or we're going to now define what sine of angle V is equal to. Well, we define this as the opposite leg over the hypotenuse. Which my naming convention is O over H. For tangent of angle V, that is the opposite leg over the adjacent leg, which is O over A. Then lastly, we have secant of angle V, And for this one, we denote as the adjacent leg over, oh, my apologies, it's the hypotenuse over the adjacent leg, which is h over a. So these functions are defined with in reference to angle V. Now we have the co-functions or the complementary functions. They are defined with the same mechanics, except they're defined with the complementary angle W. So we can think of cosine as the same scheme as sine, except in reference to the complement angle, but we're going to retain these labels of O, A, and W. What do I mean by this? I have cosine of angle V is equal to the sine of angle W. Well, if I have the sine of angle W, I'm going to be looking at the opposite leg and the hypotenuse. I'm going to keep my label naming convention, and so I'm going to label this as adjacent leg over hypotenuse, which equals A over H. For cotangents of angle V, that's the same as tangents of angle W, which equals my opposite over adjacent in reference to angle W. So keeping the naming conventions, I have A over O. So I have my adjacent leg over my opposite leg. So that's O. Sorry, that's A divided by O. And finally, I have cosecant of angle V, which is the secant of angle W, which equals hypotenuse over the opposite leg, which equals H over O. So with these definitions, we can start defining certain properties. For instance, if I look at the sine of angle V, I have O over H. I could rewrite this as 1 divided by the reciprocal of O divided by H, which is H divided by O. What is H divided by O? That is cosecant. So we have 1 over cosecant of angle V. If I had tangent of angle V, I have opposite over adjacent, which is equal to 1 divided by the reciprocal. So that's adjacent over opposite. So that's 1 over cotangent of angle V. Lastly, we have cosine of angle V, which is adjacent over hypotenuse. If we take 1 divided by the reciprocal, h divided by a, we can rewrite that as 1 over secant of angle V. Notice that we have done the same trick over and over and over again, and these facts remain true if I take the reciprocal of each of these equations. Cosecant is 1 over cosine of the same angle. Cotangent of angle V is 1 over tangent of angle V. Secant of angle V is 1 over cosine of angle V. So now that we have this, and we have basic relations between these, let's explore a little bit more about what a right angle has. Or a right triangle. With a right triangle, we have Pythagoras' theorem. And with Pythagoras' theorem, it states that leg 1 squared plus leg 2 squared is equal to the hypotenuse squared. So assigning our naming convention, we have opposite squared plus adjacent squared equals hypotenuse squared. What if we divide by h squared? We have 1 on the right-hand side here. And on the left-hand side, we can split the fraction over addition, and we get O squared over H squared plus A over H, or A squared over H squared. We can, with exponent properties, make this a fraction of O over H squared. Make this fraction be A divided by H squared equal to 1, which gives rise to, what is O divided by H? Well, that is sine. So we have sine of this angle V, and we're going to square it, plus cosine of this angle V squared is equal to 1. Now, how did I get this cosine? I took the adjacent over hypotenuse. I found what that was. That is cosine up there. And I'm going to square it because we have that fraction squared. Here's where another situation where mathematicians, we like to be a little bit lazy. with notation. And I don't want to write these parentheses over and over and over again. So I'm going to say that sine squared of angle V, this is the same as sine of angle V, that whole quantity squared. So I'm going to have cosine squared of angle V match the same convention. I'm going to write that equal to 1. There's your trig identity. We have sine squared V plus cosine squared V of the angle V, I should say, is equal to 1. Now, my claim is this is the trig function that you must memorize. And some of you who may have seen other trig functions, but you're like, hey, wait, there's a lot of functions like, or a lot of equations, 1 plus tangent squared equals to something I always forget. 1 plus cosine, oh no, is it cosecant? I forget what these equations are. There's so many co this, co that, and it's hard to keep track of all that. Well, here we took Pythagorean's theorem and we divided by h. And that's how we generated this equation here. Well, let's use that same convention of we can just divide by something to get our other identities. What happens if we divide by cosine squared? Well, we're going to get sine squared over cosine squared. So I'm going to write that now as sine of angle V over cosine of angle V. And this whole quantity is squared plus, when I take cosine squared and I divide it by cosine squared, something divided by itself, that's 1. That's equal to 1 over cosine squared of angle V. Well, now, when we look at this, we say, hey, this 1 over cosine squared V, that's like the same as 1 over cosine V squared. All right, well, what is 1 over cosine V? 1 over cosine V is secant. Because we're going to take our A over H and take the reciprocal of it. And we see that here. So we can rewrite this as 1 over secant. Or sorry, not 1 over secant. We have 1 over cosine. So this is secant squared of angle V. That's what this cosine is. What is it equal to? Well, this sine over cosine, we could rewrite as opposite over hypotenuse divided by adjacent over hypotenuse. And we're going to square this big thing and add 1. Okay. Well, if I take the reciprocal of this, I'm going to times by h over a times the top by h over a. Cancel, 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 cancel. This is now 1. And the top, we have the h's canceling, giving us O over a quantity squared plus 1 is equal to secant squared of angle V. Well, what is O over A? It's our opposite leg divided by our adjacent leg. That is tangent. So we're going to rewrite this as tangent of angle V, which by our convention of exponents, we're going to rewrite this as tangents squared of angle V plus 1 is equal to secant squared of angle V. And there's a trig identity. So what we have found here is that through one trig identity, we could get another. For the check on learning, what I want you to do is to do this, but divide by cosine squared and reclaim the other identity. Please show steps. Don't just write down the identity. Show your steps with that. All right. So now we're going to look at some specific angles. So let's say that our angle V is equal to, let's say, 45 degrees. All right. So if I was to do this at 45 degrees, we're going to have leg 1 be equal to leg 2. So we have this triangle with equivalent legs. And a hypotenuse, h, I'm going to say is equal to 1. Well, we will discuss on how to solve this in particular, but that's next section. So I'm just going to label this as square root 2 over 2 and label this one as well as square root 2 over 2. And we'll see a reason why in the next lecture video. But so using this, let's now use our conventions, and we want to find all the trig values. So we're going to look at sine of angle V is equal to our opposite leg, square root 2 over 2, divided by our hypotenuse of 1, so that's just square root 2 over 2. Our tangent of angle V is going to be our opposite leg divided by our adjacent leg, which is square root 2 over 2 divided by square root 2 over 2. Something divided by itself, that's 1. And our secant square root V of 45 degrees is equal to our hypotenuse divided by square root 2 over 2, which if we take the reciprocal and rationalize the denominator, we get square root 2. Okay. Cosine of 45 degrees, which is our angle V. That's going to be our opposite, our adjacent over hypotenuse. And we get square root 2 over 2 again, because we have square root 2 over 2 divided by 1 for our cotangent. We can also think about this as 1 over tangent. So 1 divided by 1 is 1. But if we don't do that, we could also just find what's our adjacent over our opposite leg, and we'll get the same answer. And for our cosecant, of our angle V, we can write that as our hypotenuse divided by our opposite leg, or 1 over sine, which we then can take 1 divided by square root 2 over 2, which is square root 2. A similar thing can be found for the other angles, such as theta equals 40 or 60 degrees. We could do theta equals pi over 2 radians, and those are found in the textbook, as well as we will construct a circle later on in this course, a unit circle that will have all of these relations on there. And as long as you can know that circle, the unit circle, we'll be able to rediscover what any of these values are. So the last thing that I want to cover is more of the terminology, as well as go through an example of using these equations to find something useful. So with the terminology, we have, as stated, with the trig function to a power of p of some angle, we're going to say is equal to that trig function of the angle theta raised to the power of p. Now this is where p is greater than or equal to 2. So if it's 2, 3, 4, 5, we're going to do that. If it's 1, well, we're not going to put a 1 there because 1 doesn't do anything. Anything to the power of 1 is just itself. Technically, this works for negative exponents. However, there's a little hiccup with that. If I wrote sine, if I had sine of theta to the negative 2, well, what this means is 1 over sine theta squared. Well, we know what 1 over sine theta is. That is cosecant. So instead of writing sine to the negative power, I'm just going to have cosecant squared theta. So if you want in any of these exercises and you see a cosecant or cosecant squared or something like that, you could write it as just 1 over sine to the appropriate power. Similarly with any of the other trig functions. And you might be thinking, oh, well, I've seen this before. Sine to the negative first of theta. Well, it's not to the negative first for the same reason being, if it was actually sine to the negative first, I would rewrite that as cosecant. So instead, this is lazy notation for sine inverse, or as I prefer, and you'll see me write it this way, arc sine. Now, I will admit that I've been using a little bit of abusive notation here with this angle of theta. What this really is meaning is that this isn't theta as like a angle at all. It's really an arc length, which is why you have arc sine. What is the angle that makes that arc length possible? That is what it means. However, we'll investigate this further in the next lecture video. But for now, just know that if I have sine squared or cosecant squared or anything that's like that, it is a power, not anything else. It's just think of it as the trig function to the appropriate power. That's what any of this convention means. Okay. So how can we do some arithmetic with this? Well, let's give an example. So say we have an angle is 12/13. And I want to know, no, let's not that. We have, sorry, sine of 12/13. Sorry, sine of theta is equal to 12/13. That's what I want. And I want to figure out what cosine of theta is. Okay, so I have to first think of what is an equation that relates these two. Well, I have sine squared theta is, or plus cosine squared theta is equal to 1. So let's rewrite this as cosine theta, or cosine squared theta, is equal to 1 minus sine squared theta. We don't want cosine squared, we want cosine. So we take the square root of each side, and that leaves us with cosine. Okay. So now we know what sine of theta is. So let's square it, and we get square root of 1 minus 12/13 quantity squared. This is equal to square root 1 minus 12 squared, which is 144, divided by 13 squared, which is 169. This equals square root. We need 1 minus 144 over 169. So I'm going to rewrite this 1 as 169 divided by 169. That's the same as 1. So now we can combine like fractions with the same denominator, and we have 169 minus, or 169 minus 144. That is 25 over 169. Square root of 25 is 5. And square root of 169 is 13. So I end up getting that cosine of our theta is equal to 5 divided by 13. Notice I generated this equation here. there's a list of equations in the textbook, and this is one such equation that is included. Cosine of theta is equal to square root of 1 minus sine squared theta. Well, as long as I know my base one of sine squared theta plus cosine squared equals 1, I can solve for the other. Similarly, we have the same thing with tangent, cotangent, cosecant, secant. As long as you know this one, we can derive the others. It's better for you to memorize that in terms of speed. But as far as memorization goes, memorize this and know how to get the other ones. Because when you do that on a test, and you don't have you don't have the you have testing anxiety, you don't have the composure that you normally would do on an assignment, take a little bit of time and verify your results so that you know exactly what you're getting and that you know it's the correct answer instead of, did I use the right formula? And so from here, now that we have cosine, we have sine, if I ask what is tangent, well, we could just put them together and say, all right, sine theta over cosine theta is equal to tangent theta, as we found before. So I put these two together, I have 12 over 13 divided by 5 divided by 13, and I get, I'm going to times by a reciprocal, 13 over 5, 13 over 5. This bottom cancels to 1, 13 cancels, and I get 12 fifths equals tangent of theta. So now I want to say, what's cotangent of theta? Well, cotangent of theta is 1 over tangent of theta. So we get 5/12. What if I want secant of theta? Well, secant is 1 over cosine. So we have 13 fifths. And finally, cosecant of theta equals 1 over sine, which is 13/12. And now I found all my trig identities with respect to the same theta. I did not change my reference angle. So in this, we've covered basic trig equations. We've covered terminology. We covered trig functions and right triangles. Thank you for watching and have a great day.